In this video we're going to be working with the Koch curve. It was discovered in 1906 by Helge von Koch. The Koch curve is a sequence of figures that are modified step by step. So we start with an equilateral triangle, and we call this triangle F1. Now in the second step, what we're going to do is divide every side of the triangle on 3 equal parts. So if the sides of the original triangle were of 1 unit, then in the second step they will be of 1 over 3. And what we will do is grab the middle section and draw another triangle that is also equilateral. We do this in every side of the triangle. And now we will delete these sections from the original one. We call this whole figure F2. And now we do the same. Now we have all these sides of length 1 over 3, and we'll divide all of them into 3 equal pieces, each of size 1 over 9. And in the middle line, draw an equilateral triangle. And again delete all the middle sections from the previous shape. So then this figure is called F3. And now we do the exact same thing on every other side of the triangle, and we're gonna have something like this. And this figure would be F3. And so we continue like this infinitely many times. Now we have a sequence F sub n of figures, and from this sequence we can get to more, P sub n and A sub n. P sub n will be the sequence formed by the perimeter of all the figures, and A sub n by the area. So what we're going to do in this video is prove that the limit of the perimeter when n tends to infinity is infinite, but the limit of the areas A sub n is not infinite. So what this is telling us is that we have a bounded figure with infinite perimeter. Let's start by calculating the perimeter. So P sub n is the perimeter of F sub n. P sub 1 is going to be 3, because we had a triangle of sides 1. Then P sub 2 is going to be, and let's now think of this for a moment, we have on each side of these ones, we divided it by 3 and created like this. So we have 1/3 each side. And we have 1, 2, 3, and 4. So it's 4 times 1/3 on each of the sides of the triangle. And we have 3 sides, so times 3. And this is equal to 4. And now let's think about P3. We had this in the first step, and now in each one of these we do the same. So this time we have 12 times 4 divided by 9, because the sides are now 1 over 9, times the 3 sides of the triangle, which gives us 16. So when we continue, we're going to have that P sub n is going to be first the measure of the sides. This will be multiplied by the number of sides, and then it will be multiplied by 3, because we have 3 total sides in our original triangle. Now the measure of the triangles is 1 in P1, 1 over 3 in P2, 1 over 9 in P3, and it will be 1 over 3 to the n minus 1 in P sub n. The number of sides will be 4, this is the number of sides we make for each side, times 3 times 4 to the n minus 2. And all this is multiplied by 3. So we have 4 times 4 to the n minus 2 times 3 times 3 divided by 3 to the n minus 1. So this is 4 to the n minus 1 times 3 squared divided by 3 to the n minus 1. We can write this as 4 to the n minus 1 divided by 3 to the n plus 1. And so it's clear that the limit when n tends to infinity of p sub n, that is, the limit when n tends to infinity of 4 to the n minus 1 divided by 3 to the n plus 1, is equal to infinity. Now let's calculate the area. Given any triangle that's equilateral, let's say this triangle has sides of length a. To calculate the area, we need the height. And the height is going to be the square root of the hypotenuse is a squared minus, this will be a over 2 squared. This is the square root of a squared minus a squared over 4. Now taking common factor a, we have this a times the square root of 1 minus 1 over 4, which equals to a square root of 3 divided by 2. So then the area of an equilateral triangle of sides a will be the base times the height divided by 2. This is a squared square root of 3 divided by 4. Now let's think about the triangles we have. In F1 we have one triangle of sides A equal to S. This is the area will be A1 equal to S squared square root of 3 divided by 4 using this formula. On F2 we have the area from F1 because we have this whole triangle and we have to add 3 smaller triangles. So we have F1 plus 3 triangles of sides A equal to S divided by 3. So we have the area will be the area of F1, this is S squared square root of 3 divided by 4, and to this we have to add 3 triangles, each with area S divided by 3 squared square root of 3 divided by 4. And this is equal to square root of 3 divided by 4, that's a common factor, S squared as common factor, 1 plus 3 over 9. Now on the third F we have again everything we had before, and we have to add all these smaller triangles. So F3 will be the triangle we had before plus 12 smaller triangles of sides A equal to S over 9. So A3 is going to be F2 is this area And now we have to add 12 times the square root of 3 divided by 4 s over 9 squared. So then a3 is equal to square root of 3 divided by 4 s squared. And here we have this 1 plus 3 over 9 plus 12 divided by 9 squared. 12 is 3 times 4 divided by 9 squared. Let's do one more step. f4 is going to be f3 plus 48 smaller triangles of sides a equals s divided by 3 to the power 3. So a4 is going to be the area we just calculated and to this we have to add square root of 3 divided by 4 times 48 times s divided by 3 to the power 3 squared. So then a4 will be square root of 3 divided by 4 s squared. We have all this term is 1 plus 3 over 9 plus 3 times 4 over 9 squared plus 48 is 3 times 4 squared divided by 3 to the power 3 squared is 9 to the power 3. And so once we've done all this, it's easy for us to realize that a sub n will have the form square root of 3 divided by 4 s squared times 1 plus the sum from n equals 1 to infinity of 3 times 4 to the power k minus 1 divided by 9 to the power k. The sum is not up to infinity, I'm sorry, it's up to n. And so what we have to do is ask what happens when n tends to infinity. For us, s was equal to 1, we can actually make it equal to whatever we want. But the thing that depends on n is the sum. So we're first going to work on the sum. We can write this as taking common factor 3, the sum of 4 to the k minus 1 divided by 9 times 9 to the k minus 1. So then this is 3 over 9, the sum of 4 over 9 to the k minus 1. And then, as the sum started from k equals 1, we have a geometric series with radius equal to 4 over 9, which is smaller to 1. And so we know that the sum from n equals 1 up to infinity of 4 over 9 to the k minus 1 is equal to 1 over 1 minus 4 over 9. So then a sub n is the square root of 3 divided by 4 s squared times 1 plus 3 over 9 times the sum from n equals 1 to infinity of 4 divided by 9 to the n minus 1. This will be the total area. And so, because we know this sum, this is the square root of 3 divided by 4 s squared 1 plus 3 over 9 times 1 over 1 minus 4 over 9. And this is the square root of 3 divided by 9 s squared times 8 over 5. So the total area is 2 times the square root of 3 divided by 5, s squared. If we equal s to 1, which was our case, we have 2 square root of 3 divided by 5. So we have a finite area, but we also say that the perimeter of our figure was infinite. And that is what is so interesting about the Koch curve.